This is the apparatus which is used to investigate the photoelectric effect. It has a plate of metal under investigation called the cathode. Another metal plate called the anode is connected via an external circuit which includes a battery, and we'll talk more about the battery later. The two plates are enclosed in a vacuum tube. Light of various wavelengths and varying irradiance can be shown on the cathode. An ammeter will indicate if electrons are ejected by reaching the anode, thus creating an electric current in the external circuit. The metal under investigation is zinc, and that is attached to the cathode as shown there. The light has zero intensity at the moment, or irradiance as we say, and remember, irradiance is the power from the lamp landing on a metre squared of that particular metal. The irradiance gives you a measure of the energy per second falling onto the piece of metal. So at the moment it's at zero, it's off. The potential difference across the cathode and anode is set to be 0 volts, which means the electrons, if they're ejected from the metal plates, will not be given any extra push to make them reach the anode. Now we can put the lamp on now for a moment at half intensity, there it is there, and it's shining in infrareds, which really heat, and you're not getting any electrons ejected. We can go down the spectrum into the red area, nothing. If we increase the irradiance, still nothing. We can go into the yellow part of the lights and increase the irradiance, still nothing happening. We can go further down, we're decreasing the wavelength, and remember, when we decrease the wavelength, we increase the frequency of the light used. So as we increase the frequency, still nothing at all. Into the blue area, nothing. Into the violet area, nothing. Even though we pump up the irradiance, nothing at all. No electrons given off. We can see that the current is zero. If we go into the ultraviolet area, we get 356 nanometers, still nothing given off. 342, nothing. 326, nothing. We can increase the irradiance, still nothing. If we go down further, decreasing the wavelength, which means increasing the frequency, you can see as we get closer and closer down, still nothing. We're at 290 nanometers of wavelength of light and still nothing there. 287, and as you can see, we're now beginning to get electrons ejected from the zinc plate. And that's registered when the wavelength is 287 nanometers. Now, the electrons have got enough energy to get right across the plate as it stands now. Now, if we increase the radiance of the lights, make light with more energy per second, per metre square landing on it, we're going to get more electrons given off, but in many ways I don't see any big change in the energy, which we'll come across that a wee bit later. So a key point for the moment is that you're only going to get electrons ejected from the zinc metal below a certain wavelength, or in other words, above a certain frequency. So here we have the lights at a certain wavelength, certain frequency, shining onto the zinc, and you can see no photoelectrons are being released, which must mean that the frequency of the light used is definitely below the threshold frequency. Remember, the threshold frequency is the frequency of the light which will start to eject the photoelectrons. Threshold means like the door, like entering into the door. Now you can actually see that in a little graph I'm going to highlight to the right here. You can see at the moment there's no electrons given off, and the energy of the electrons is going to be zero. But if I work my way down, you can see that once I get to a certain frequency, then things take off. You can see that the energy of the electrons is beginning to increase if I increase the frequency. So that's a very important fact. It seems to be that the energy of the electrons given off is directly proportional to the frequency of the light used. So the energy seems to be directly proportional to the frequency. And you can see if I reduce the frequency, which means increasing the wavelength, you can see that blue dot going way back down to the threshold. So the key point is this: electrons will be ejected at or above a certain threshold frequency, and that the energy of the electrons given off is directly proportional to the frequency of the light which is shining on the metal under question, as indicated by that little blue dot, rising up, increasing energy with the higher the frequency of light. So here we have photoelectrons being emitted from the zinc plates by light of wavelength 221 nanometers. So we can confidently say that that light has got a frequency higher than the threshold frequency necessary for the ejection of the photoelectrons. Now, the important part we're going to study here is that you can see there's going to be a range of the photoelectron energy. Not all the photoelectrons have got the same energy. They seem to have a high energy, and some have got a low energy, and some are in between. So there's a range of energies. And we can see this perfectly well if we actually put a potential difference between these two plates, which I'll do at the moment. So if I put this down to here, you can see I'm making the plate on the right much more negative, and the plate where the electrons are being ejected from much positive. So you can see that some reach beyond halfway of the tube, others don't, and that tells us a very important fact. It tells us that there's a range of energies of the ejected photoelectrons. You can think of, if you turn your head to the side, I know it might be a bit awkward, but if you turn your head to the side, imagine you're standing watching a crowd of people throwing hats or balls into the air. Then they're not all going to have the same energy, because if they did, they'd all go to the same height. So therefore, we can deduce from all the hats being thrown into the air or balls being thrown into the air, if they go to different heights, we can deduce that they will have different energies. The high energy ones released will go higher, the low energy ones released will go a smaller height. So it's the same with this electric plate system here. You can see that because I've arranged the plate on the right to be negative and the plate on the right to be positive, you can see that it's pulling the electrons back. It's almost like gravity, and the electric field is pulling them back towards the positively charged plate. But the striking thing we can see from that simulation there is that there's going to be a range of photoelectron energies, ranging from the highest, which is getting to this point here, to the lowest, some only getting it slightly above or coming back less than halfway. Now, even though I increase the radiance of the light to almost double that, you can see it's having no effect on where the maximum energy photoelectrons reach, which tells us another important fact, that the intensity or the radiance of the light, the amount of energy per second arriving on that plate per meter squared, has no effect on the energy of the photoelectrons ejected. The summary of the photoelectric effect so far. We know that light of a frequency above a certain value will eject electrons from the surface of a metal. We also know that light with frequency below a certain minimum value will not eject electrons from the metal. So there seems to be what we call a threshold frequency, above which electrons will be ejected from the metal, below which no electrons will be ejected from the metal. And the third point here, the ejected electrons are called photoelectrons, and if light shines on the metal plate above a certain threshold frequency, then the photoelectrons emitted will have a range of kinetic energy. The photoelectric effect could only be explained by the particle nature of light. So far we've understood light to be in terms of waves, because it interferes, it reflects, it diffracts, therefore it's a wave nature. But the photoelectric effect comes along and just disrupts that argument, because waves don't knock things off things. Waves tend to lift particles up and down, or move them back and forth. Here we have electrons being emitted from a metal when light shines on it. And the only way to help us describe that is to say that the light which is shining on the metal, which is doing the ejection of the electrons, is made up of particles. And these particles of light are called photons. And what's more, these particles carry with them a certain amount of energy, and that energy is directly proportional to the frequency of the light in which they belong. So here we have the situation here. Each photon carries a certain amount of energy proportional to the frequency of its associated light. And that constant of that proportionality is called Planck's constant h. And that means we come up with the equation E equals hf, h being Planck's constant, f being the frequency of light, and that little equation there tells us the energy of each photon of light of a particular frequency.